Hello everyone, so here are your notes for 10.1, lines and segments that intersect a circle. Now, there is a list of definitions below. I don't believe that this is the first time you're seeing them. However, if you're not quite familiar with some of them, go ahead and pause the video here and copy all of these definitions down. Okay, so I'm not necessarily going to go over each and every single definition, but we will go ahead and label every single part onto the circle as well as make a couple of other notes. Now, the first thing that I want to talk about is the actual definition of a circle. It says all points equidistant from a given point. So, what this is saying is that if we were given a single point, for example, let me go ahead and zoom out for a moment here. If we were given a point somewhere in space, let's pretend that from this point, let's measure 3 inches. And then once we measure 3 inches, we're going to go ahead and mark another point 3 inches away from the original one. Now, what we can do is we can go ahead and we can measure another 3 inches in a different direction, mark another point, and we can continue to do this until we basically have a circle. Now, we know, of course, that there are an infinite amount of points. And so there on the circle itself, there actually is an infinite amount of points, which creates this circle or curve that you see in front of you. But this is the true definition of a circle. All right, so that being said, this is how we name a circle. We use the center point. The center point for this particular here is point A. So here's how we write it. We write it with a dot and a circle around it with the center point. So this circle here, we name it as circle A. All right. And then the other parts of the circle. The segment that connects the center point and any point on the circle is called the radius. And then we also have a segment that connects any 2 points on the circle. For example, EF right here, this segment is called a chord. Now we have a very special chord, this one here, CD. This is technically a chord because it does connect 2 points on the circle. However, this chord passes through or intersects the center. And because it intersects the center, segment CD is actually a diameter. All right, and then we have 2 lines that are passing through the circle. In other words, completely kind of cutting through it or intersecting it. So the line that we have on the top, HI, it actually passes through the circle twice. As we can see here, 2 points of intersection. This line is called a secant. And then last but not least, we have a line that actually only intersects the circle at 1 point. This line is called a tangent. All right. Now, one last term that I want to bring to your attention is the point where the tangent line intersects your circle. This point has a very special name. It is called the point of tangency. All right. So those are all of our parts of the circle, all of the lines and segments in the circle labeled up for us. One other thing that I want you to keep in mind is that the radius is congruent to every single other radius in the same circle. So if I were to measure AB, AD, and AC would be the same. This has to do with the definition of the circle because, again, all of these points on the circle are equidistant or equal distance from the center. All right, so let's go ahead and let's cover our first theorem. But actually, before we go ahead and cover that first theorem, there's a term here that I want to quickly explain. There's a statement or a sentence called a conditional. Now, what a conditional is an if-then statement where the condition must be met in order for the conclusion to be true. So the basic idea is that you have some sort of condition, some sort of requirement. And then once that condition or requirement is met, it's been checked off, it happens, then your conclusion happens as well. Here's an example. Here's an if-then sentence. If it rains, you will need an umbrella. Okay? So this is almost like a little bit of common sense, right? If it's not going to rain, we don't need an umbrella. However, put in a sentence in the following form, the condition is that it rains. And so if this condition is met, then your conclusion will be true. So in a sense, this is just a little bit of logical thinking. For example, let's pretend that right now it's actually not raining. So the condition, it rains, has not been met. Therefore, you don't need an umbrella. The conclusion is not true. However, if it actually is raining outside, the condition has been met, which means that the conclusion is that you will need an umbrella. So we're going to use this idea in the following theorem. So the theorem is that we have a tangent line to the circle theorem. Here's what it says. A line is tangent to a circle if and only if the line is perpendicular to a radius. Now, it's definitely been quite a while since we used this word perpendicular. Keep in mind that perpendicular are two lines, two segments, whatever they are, but they form right angles. Right? 90-degree angles is what they make. So that's what we're looking out for. Now, this sentence here has a funny little phrase in it. It says if and only if. So here, there is a condition and there is a conclusion. However, you can actually reverse those conditions and conclusions because of the if and only if. So let's take a look at what that means. Let's look at this picture. I have a circle. The center is J, so we'll call this circle J. There is a radius, JK. I have a line M, and it seems to be passing through point K. Now, here's the thing. We don't know for sure if line M is a tangent or not. They don't quite tell us. And there's no indication that I have right angles. Nothing is marked. So here's what's going to happen. The condition is that line M is a tangent to circle P, to circle J, excuse me. So here's what I mean. In the problem, they might tell you that a line is tangent to the circle. So this is the condition, and it has been met. Line M is tangent to circle J. If this is true, if this condition has been met, then we are allowed to make the conclusion which says that line M is perpendicular to segment or radius JK. Okay. Now, if they don't tell us in the problem, though, they do not tell us that the line or the segment is tangent to the circle, then we cannot assume that we have perpendicular lines or segments. We're only allowed to make this conclusion if the condition has been met. Now, let's take a look at the reverse of this. Let's change the condition. Now, the condition is that line M is perpendicular to segment JK. They might tell us in the problem that JK and line M are perpendicular. They might also mark the angle with a right angle mark. These are just two different ways for us to be able to determine if the line M is perpendicular to segment JK. And again, if this is true, then we are allowed to make the conclusion that line M is tangent to circle P. Okay, so let me zoom out and just quickly rephrase all of this once more. There are technically two conditions, but really it comes from one sentence. So first condition, we know that line M is tangent. The conclusion, line M is perpendicular to the radius. When we swap that, what happens is that we don't know if line M is a tangent yet. That's not true. We don't know that yet. But what we do know is that line M is perpendicular to a radius. Once we know that, then we are allowed to make the conclusion that line M is tangent to the circle. Let's go ahead and let's use this in an example, and hopefully it'll make a little bit more sense. All right, so in our example here, here's the question. It's asking us, is segment ST tangent to circle P? So this is what I was talking about earlier. We don't know if segment ST is tangent to the circle or not. We have to be able to prove this. So, first thing, our conclusion, or what we're trying to find out, is two different choices. Either yes, segment ST is tangent to circle P, or no, segment ST is not tangent to circle P. Okay, so these are two different conclusions we can make. Now, in order to make these conclusions, though, in order to figure out whether segment ST is tangent or not, from the theorem earlier, the condition that needed to be met said that the segment ST needs to be perpendicular to the radius. The radius here is segment TP. So this is the condition that needs to be met in order for us to make the conclusion that segment ST is tangent. In other words, when I look at the picture here, TP and ST need to form a right angle. Now, what you'll notice is that in the picture, we actually have a triangle. And if ST and TP form a right angle, that means that we have a right triangle. So what we're actually proving here, or what we're trying to prove here, is that triangle STP is a right triangle. Because if it is a right triangle, then the segment is going to be tangent, because I will have the perpendicular segments that I wanted. So in order to try and prove that this is a right triangle, they provided us with 3 side lengths. And if this was a right triangle, it would satisfy the Pythagorean theorem. So that's what we're going to go ahead and use to figure out if this is a right triangle or not. Now, remember once more that the variable c represents the hypotenuse. The hypotenuse is the longest side of a right triangle. So my longest side in the triangle is 37, and that's the number I'm going to substitute into c. And then 35 and 12 can go in place of a or b, and it doesn't matter which one is which. So I'll get 12 squared plus 35 squared is equal to 37 squared. We can go ahead and put this into a calculator. 12 squared is 144, plus 35 squared, which is 1,225. And this is equal to, or rather we're trying to check to see if this is equal to, 37 squared, which is 1,369. When I add the two numbers on the left side, it actually does become 1,369. And this is in fact equal to 1,369 on the right side. So here's what I've basically done. I verified with the Pythagorean theorem that triangle STP is a right triangle. And because triangle STP is a right triangle, this in turn means that segment ST is perpendicular to TP. In other words, I have a segment that is perpendicular to a radius. That in turn satisfies the conclusion that yes, segment ST is a tangent. So there's kind of a lot of thinking here, but just to go over it one more time. The question was, is segment ST tangent to circle P? Because we were trying to figure that out, we needed to see if we can prove that the angle here is a right angle. Well, if we have a triangle, that means that that would make it a right triangle. And that's where we use the Pythagorean theorem. Because the Pythagorean theorem only equals on both sides if you have a right triangle. And because we were able to prove that the triangle is a right triangle, this means that yes, my segment is in fact tangent. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, so go ahead and check over your answers. Again, we use the Pythagorean theorem, but this time you have to be a little bit careful because the 2 only represents the part of the line or segment that is on the outside of the circle. The part that's inside the circle, this is technically a radius. And CD is also a radius. And all radii are congruent or have the same lengths. So if CD is 3, that means that the segment piece inside the circle right here is also going to be 3, which means that the total length of CE is going to be 5. So, substituting everything in, again, we're trying to check to see if both sides of the equation are equal. That's why you see these question marks. But I verified that yes, they are in fact equal, which leads me to this conclusion that CD, segment CD, is perpendicular. This symbol means perpendicular to segment DE. And so this allows me to finally make the conclusion that segment DE is tangent to circle C, because the condition that a segment or line is perpendicular to a radius has been met. All right, let's take a look at another example. So in example 2, they tell us that point B is a point of tangency. What they want us to do is they want us to find the length of the radius r. So here's r, here's another r. Again, all radii are congruent. Now, when we're looking at this picture, there's a few things that we kind of need to know in order to figure out how to get started. First of all, this is a triangle. Now, what kind of triangle that is comes from the problem. The problem told us that point B is a point of tangency. Now, a point of tangency is where the tangent line intersects your circle. So if point B is a point of tangency, that means that AB, which intersects the circle at point B, is a tangent. And from the theorem earlier, we know that if you do have a tangent, that means that the tangent is perpendicular or makes a right angle with the radius. The radius here is CB. So segment AB is perpendicular. They form right angles with segment CB, the radius. And if we make a right angle with these two segments, this means that triangle ABC is a right triangle. So, because triangle ABC is a right triangle, and I'm working with the sides of the right triangle, what I'm going to have to end up using is the Pythagorean theorem. Now, the Pythagorean theorem is going to be just a little bit different this time. What I'm referring to is the substitution. When we look at a right triangle, we always need to try and figure out, okay, which side is the hypotenuse? Which side will be the side that we will substitute in for C? When we look at our right triangle here, the side that's opposite from the right angle is side AC. Now, one thing that's really important to note is the fact that AC is made up of two parts. There is a segment that is on the outside of the circle, and there's a segment that's on the inside of the circle. That segment on the inside is the radius. Now, if I take the radius and I add it together with the segment that's outside, that gives me the whole hypotenuse. This is technically the segment addition postulate. So, what I substitute in for the hypotenuse is actually 50 plus r. So let's go ahead and do just that. So on the right side of the equation, once more, this is going to be 50 plus r quantity squared. Now, I'm squaring the whole thing because, again, keep in mind that C is the entire hypotenuse, and the entire hypotenuse is 50 plus r. And then for A and B, it doesn't really matter what we substitute into where. I'm just going to go ahead and call 80 feet A. So on the left side of the equation, we get 80 squared plus b squared, but b is the other leg of the right triangle, and that is actually r. It's the radius of the circle. So I am actually going to replace b with r. All right, so let's go ahead and let's actually begin solving this. On the left side of the equation, 80 squared becomes 6,400 plus r squared is equal to 50 plus r times 50 plus r. Now, if you think back to algebra, there was a way for us to multiply polynomials. You can FOIL first, outside, inside, last, or you can draw those little rainbows. I like to call them rainbows anyways. So here's how we're going to do it. I'm going to go ahead and draw my rainbows. I'm going to start from 50 and go to the other 50 in the other term, or sorry, the other set. And I'm also going to draw another rainbow arc from 50 to the other r. Now from the first r, I'm going to draw it to the 50 on the right side, and I'm going to draw another arc from r to the second r. Now what we're actually doing here though is multiplication. So let's go ahead and let's multiply every single one of those following the arcs. So the first one that I drew was from 50 to the other 50, which is 50 times 50. That gives us 2,500. And then we had to go ahead and multiply the 50 with the second r. That is going to give me 50 times r, 50r. Then we went ahead and multiplied r with the second 50, r with the 50 on the right side. That again is just another 50r. And last but not least, we needed to multiply our two r's together. That gives us r squared. And we didn't do anything to the left side, so let's go ahead and rewrite that. And now, again, algebra, we need to go ahead and we need to get all of our variables onto one side of the equation. I have a lot of r's on the right side of the equation, so let's go ahead and let's move this r squared to the right side. How we do that? We need to subtract r squared on both sides of the equation. So my r squareds on the left side are going to cancel out, but here's the thing. I have an r squared on the right side, but I'm subtracting an r squared. So this actually cancels out as well. And here's what we are finally left with. 6,400 is equal to 2,500. And I can go ahead and combine like terms because I have 50r and 50r. That gives us a total of 100r. All right, from here, relatively straightforward algebra. I'm going to go ahead and subtract 2,500 on both sides of the equation. On the left side, 6,400 minus 2,500 is 3,900, and this is equal to just 100r. Last but not least, 100 times r means that we need to divide by 100 on both sides. And last but not least, we finally get that 39 is equal to r. All right, so that right there is how you use the theorem that a tangent line is perpendicular to a radius in an example to solve for the length of the radius. All right, so go ahead and pause the video here and see if you can give this one a try on your own. All right, go ahead and check over your answers, specifically what you substitute in for C, because again, the hypotenuse is made up of two different segments. There's a segment that's r units long, and there's another segment that is 18 units long. So we need to add those together to get the hypotenuse. Make sure that when you are multiplying, you multiply every single term in one with the other. And then we just finished solving for r, and we get that r is equal to 7. All right, let's go ahead and let's cover one more theorem for today. This theorem is called the external tangent congruence theorem. It's kind of a mouthful, but the concept is actually very straightforward. So here's what the theorem says. It says that tangent segments, because yes, you can have more than one tangent segment to a circle. Tangent segments from a common external point are congruent. So let's kind of break this down. We have tangent segments. The ones in the picture that are tangent are RS and TS. These are tangent segments. If they come from a common external point, in other words, we have a point, and this is where our tangents come from, and they are common, as it is here. That means that our two segments are congruent. So this is kind of like another condition where the condition is that your tangents have to come from the common external point. And then if this is true, what we are allowed to conclude is that RS is congruent to TS. Again, this is only true if they come from a common point. If there were two different points, for example, if it said maybe RO and if it said TL and there were two different points, we cannot assume that those two segments are congruent. All right, so let's actually use that in an example. In example 3, it says that segment RS and segment RT are tangent to circle C. They want us to find the value of x. So, first thing that we need to notice is the fact that RT and RS, first of all, they are both tangent, as is denoted by the problem. But the other thing that we also notice is that they come from, or they have, a common external point, R. So if this is the case, that means that RS and RT are congruent. So I can go ahead and mark them. And let's go ahead and write that statement down. RS is congruent to RT. Keep in mind again that the term congruent means that they are equal in length. They are the same. So this allows me to substitute or write an equation that uses the lengths of the two segments. My two lengths are 3x plus 4 and 28. So I can write it as 3x. Just let me substitute incorrectly for the right side. 28 for RS. And I can substitute in 3x plus 4 for RT. So once we have this substituted in, then it's just a matter of solving using algebra. So solving for x, I'm going to go ahead and subtract 4 on both sides of the equation. 28 minus 4 is 24. This is equal to just 3x because my 4's have canceled out. Then I need to go ahead and divide by 3 on both sides to finish solving for x. 24 divided by 3 is 8, and this is equal to x. All right, go ahead and pause the video here and see if you can give this one a try on your own. All right, so for this one, if you remembered how to set up the equation, it's actually only one step and relatively quick to solve. Now, one thing that I want you to keep in mind is that for some reason, this picture did not have a common, or the point here, the common external point, it wasn't labeled. So feel free to label it on your own. I went ahead and called it Q so that I can write the statement MQ is congruent to NQ. And because I know this, I can say that the length of MQ, which is x squared, is equal to the length of NQ, which is 9. Because it says x squared, I need to cancel out the squaring. So we went ahead and square rooted both sides of the equation. We get that x is equal to 3. All right, so that is it for your notes for 10.1. Thank you very much for watching.